cloud. Okay. So now I want to start discussions about Poisson regression. Okay. So I cannot finish all of these things, but let me start discussing some background. Okay. So Poisson regression. Poisson regression. So his name is Denis Poisson, a French mathematician, statistician. He gave these distributions, I think, around 17th to 18th century, something like this. It has a mathematical formula like this: x equal to x e to the power minus lambda, lambda to the power x divided by factorial x. Okay. So what is the x and what is the small x? Can anyone of you tell me? Capital X. Capital X is the random variable and small x is a specific value of a random variable. Okay. So this is the Poisson distribution. So in statistics, there are two types of distributions known as the discrete distribution and continuous distribution. Okay. In statistics, there are two types of distribution: discrete distribution and continuous distribution. So discrete distributions means x value always integer value or discrete value, and continuous distributions means x value is in a continuous scale, quantitative scale. Okay. So there are two probability distribution: discrete probability distribution, discrete probability distributions, and there is a continuous probability distribution. Okay. In statistics, there are two types of distributions. This is known as the discrete probability distribution or continuous probability distributions. Probability distribution. So Poisson is a discrete probability distribution. Clear, right? So there are two criteria that need to be satisfied if a mathematical function two criteria that needs to be satisfied if a mathematical function one to be a discrete probability distribution or continuous probability distribution. Discrete probability distributions also known as the PMF. That means probability mass function. And CPD, also known as the probability density function. Clear? Suppose one day in the morning, you wake up and you write a mathematical equation and you are claiming that this is a probability density function or probability distribution function. Someone walking in the corridor, he write a function, he showed me and said that this is a probability function. Then immediately I will check two characteristics. One is f of x or p of x. So f of x is written for the continuous, p of x is easily written for the discrete. First condition is they must be greater or equal to 0 for all values of x. This is the first criteria. Someone write a mathematical function and he said that this is a probability mass function or probability density function. Then I immediately check by plugging the values that whether the function is a positive or not. Second, summation or integration. Integration for the continuous and summation for the discrete equal to 1. Summation of px equal to 1. Take a look. Two criteria. That means the function itself always positive. The function must be positive for all values of x. And when the all functional value added, it add up to 1. These two conditions must be satisfied for a mathematical function to become a probability mass function or probability density function. Clear? In statistics, there are two types of probability distribution. These are known as probability mass function or probability density function. Probability density function is for the continuous variable and probability mass function are for the discrete variable. Okay? So now, Poisson give this formula equal to e to the power minus lambda, lambda to the power x, factorial x, and he also said that for these values of x, this function satisfied these things. Probability of x greater or equal to 0. Number 2, sum of px equal to 1. Okay? He defined these things. Any question? Okay. Any question? So he further said that lambda is greater or equal to 0. Okay? He further said lambda equal to 0. After these two conditions, if you plug in there, then these two conditions will be satisfied. Okay, let me check these two things. First of all, plug any value of x and lambda, it is always like this. If you plug x equal to 0, then this is 1, right? If you plug x equal to 0, then it is 1. If you plug lambda equal to negative or positive, this is positive. This is whatever value you will plug in there, x and lambda, this is always positive. From here and here, whatever value you will plug in there, it is positive. Whatever value you will plug in there, it is positive. Okay? Whatever value you will plug in there, this is positive. Do you understand? First condition satisfied, right? Are you still thinking? Whatever value of x and lambda, if you plug in there, that condition is satisfied. Positivity conditions. Second condition I want to check. I want to sum of p x equal to x, and x takes value 0 to infinity. Okay, x takes value 0 to infinity, and then what will happen? Infinity, x equal to 0, e to the power minus lambda, lambda to the power x over factorial x. Okay, so now plug x equal to e to the power lambda is a constant, so I take it out. If I plug 0, then I got 1. If I plug 1, that I got this. If I plug 2, then I get this. If I plug 3, then I got this, all the way like this. Okay, and then e to the power minus lambda, this is what? This is the definition. This was defined. This is equal to e to the power lambda. E to the power x is defined as 1 plus x over factorial 1, x square over factorial 2, x cube over factorial 3, and it will go all the way. Remember, there is no derivation for this. This is the definition. This is derived. This is the definition. This is defined. I can speak a lot about this mathematics, why this defined, why this come into an existence. Okay, so this and that equal to what? E to the power 0, which is equal to 1, right? Understand? So two condition is satisfied.
Excuse me, Professor. Is that lambda or x?
Is the ugly lambda.
The numerator. Is it lambda or x?
It is a
on the second last equation.
Here.
Is it lambda or x?
This is.
No, the upper one, the one in the rectangle.
Which one? This one? This one?
Yes, that one. Is the numerator lambda or x?
This is the ugly lambda. Lambda.
Lambda. Okay, thanks.
My handwriting something is not good. So this is equal to exactly that. Okay, this is equal to exactly that. So this is the formula defined. This is a definition. If you open a real analysis book or any calculus book, this is clearly written definition. It is defined. It is defined wherever you will go. It is defined in this format so that people will have a unique logarithm system. Why? See, this is the definition of log, right? So e to the power x equal to y. Okay, e to the power x equal to y, and log of e to the power y equal to x. This is the formula, right? For example, 2 to the power 4 equal to 16, right? And log of 2 to the power 16 equal to 4. Understand? This is the way log is defined. So when log was defined and all of these things was defined, around the people, while are you using what base? What is the base of your leg? 2 base, 10 base, 15 base, 13 base, people are started fighting. They said, well, come to one point. We will want to define something that we will call natural log. So then they have defined, okay, let us define these things. E to the power x equal to 1 plus x over factorial x square over factorial 2, x cube over factorial 3, all the way down. So now this is the natural base logarithm. So now they have defined like this way. Clear, right? So suppose after doing all of these things, you get a number, suppose a. Okay. So now how can you do that? Log of e to the power a equal to x. Okay. Log of e to the power a equal to x. Now what you will do? You will do e to the power x equal to a. That is the logarithm formula. Clear, right? all over the world, people are started fighting. You two base leg, 10 base leg, 5 base leg. So let us. So when the people say natural log, immediately say that this is the formula. So remember this. This is the definition. Okay. This is the definition. Okay. Now, one silly question I want to ask you. Why factorial 0 equal to 1 and factorial 1 equal to also 1? Why should I believe this? Some people say something. Why should I believe on? You understand? Why factorial 1 equal to 1, factorial 0 equal to 1? Listen, only two scenarios, only two cases, factorial 0 appears. Only two cases. Factorial 0 appears. How? Number one, if you select all from all, or if you select none from all. Okay. For example, suppose you have 10 marbles, right? So you are choosing 10, choose 0. So that means factorial 10, factorial 0, 10 minus 0, right? Factorial 0 is appearing, right? Okay. Now, I want to show you if you choose nothing. So that means this is none. If you choose all, 10, choose 10. So factorial 10, 10 minus 10, factorial 0, right? So now this is equal to 1, that is equal to 1, right? Right? Even if you try it, the permutation formula, 10, what happened? I don't want to miss that. Oh my goodness, that is gone. Yes. Okay, let me open another one. That what document is gone? Insert. So I am discussing these things. So down the road, if you have a question, so you can answer these things. So you have seen 10 choose. So now I have a 5 pen. Now I am going to give you visual example so that you will never forget. Understand? Why factorial 0 equal to 1? Take a look. I have 5 pen. Draw. I have pen number 1. I have pen number 2. I have pen number 3. I have pen number 4. I have pen number 5. I have 5 pen. Understand? 5 pens I have. I am not touching this pen. I am not removing this pen. I am not shifting this pen. Okay? So that means I am 5, choose 0, right? I'm not touching this pen. I'm not removing this pen. I'm not shifting this pen. So this 5 pen stay in this format forever, where blue is in the first position, pink is in the second position, green is in the third position, black is in the fourth position, orange is in the fifth position. In this format, they can stand forever only one way, right? That is the only one way, right? So 5 choose 0 equal to 1, factorial 5, factorial 0, and 5 minus 0, like this. This is mathematical computations, right? And this is the visual inspections. The 5 pen can stay in this format forever, right? If I do not remove them, do not shift them, do not move them. So in order to this computational technique work for all numbers, this factorial 0 equal to 1 must be considered. Otherwise, this permutation and combination formula will not work. This is a worldwide agreement. That factorial 0 equal to 1, if we consider, and that is also rational. If you choose all of these, 5, now see, I choose all 5 of 5, right? If I choose 5, choose 5, 5 choose 5 equal to also 1, right? If I choose all of these 5, then all of these 5 can be chosen only one way, right? All of this can be taken only one way. Like some people say, I'm not a crazy, but I want everything. Okay. If some people say that I'm not crazy, I want everything, that means he want all the 5. All the 5 can be taken only one way. That could be done by using this formula. So that is why there is a worldwide agreement y factorial 0 equal to 1. Even if you are not convinced with these things, then you have to come up with new formula, new permutation and combination formula. If you do not, if you still disagree, I don't want to have factorial 0 equal to 1 and factorial 1 equal to 1. Yes, come up with new formula, then we will accept you. Okay. So the reason I discuss these things, the factorial 1, because Poisson distribution has this. So this is the Poisson distribution. To the power minus lambda, lambda to the power x over factorial x, and under these conditions, x takes value 0, 1, 2 up to infinity, and lambda takes value greater or equal to 0. Okay, this is what Poisson distributions I discussed. I showed you the 2 characteristics for a mathematical functions to become a probability density function or mass function. A mathematical functions must satisfy 2 conditions, which is positivity and total probability equal to 1, which I also proved. Now the question is how these come into an existence. Most important questions. So did Dennis Poisson wake up in the morning and then he wrote this formula? Do you understand the question? If I come up with some mathematical functions and say that this is a probability, that people say that, well, 2 conditions satisfy, so it is a probability density function or mass function. But could you show us one example where we can use? If this question will be asked, then I have to show the practical utility. Do you understand? So what is the practical utility of this problem? How can these things come into an existence? This is a mathematical derivations. Mathematical derivation from binomial distribution, which I am going to discuss now. Binomial distribution. Poisson did not wake up from sleeping one day in the morning. There is a binomial distributions. He put some conditions on the binomial distributions. This is the binomial distribution. X equal to x and cx e to the power x q to the power n minus x. On these distributions, he assumed lambda equal to np, this np coming from here, and then he assumed n goes to infinity. With that thing, these 2 conditions has been applied on there, and then he come up with this thing. Clear, right? Denis Poisson, the French mathematician, he did not wake up in the morning and write a functions and then go door to door and knock the door. This is the probability density function. Instead, he derived it from binomial distribution. Okay, so let me discuss what is binomial distribution now. I have been discussing lot of background. Okay, so now take a look what is binomial distribution is. So I have 4 coin tossing experiment. So 4 coin tossing experiment, 2 coin I want to top in the column HH, HT, TH, TT, and I want to put in here HH, HT, TH, and TT. These are the 4 coin tossing experiment. Okay. Now this is HH, HHHT, HHTH, HHTT. Okay, HTHH, HTHT, HTTH, HTTT, then TH, HH, TH, HT, THTH, THTT, then TT, HH, TT, HT, TT, TH, TT, TT. Okay. Now take a look. X equal to number of heads. So now, if you plug X equal to 0 head, this is the X equal to 0 head, right? So that is equal to 1/16, right? Then I want to put X equal to 1 head. X equal to 1 head, this is the 1 head. So that means 4/16, right? Now I want to put X equal to 2 head, which is equal to 6/16. So X equal to 2 head, X equal to 2 head, right? Now X equal to 3 head, X equal to 3 head, 4/16, and X equal to 4 head, 1/16. Clear? That is that 4 coin tossing experiment. I can do it very easily. How about if I toss the coin 10 times? How many sample point? 2 to the power 10, right? So it will be 1024, I guess. Right? 2 to the power 10 of. It should be double star, I guess. Yeah, 1024. How can I compute? I toss the coin 10 times, find the probability of 7 head. Are you understanding? So there is a formula. That formula is known as the binomial formula. So that is what 4C0 and P to the power 0. P means probability of success. That means head. P to the power 0. 1 minus half to the power 4 minus 0. 4 minus 0. That is what? 1/16. So this is written as 4C1 half to the power 1, 1 minus half to the power 4 minus 1, which is equal to 4/16. That is the way it is written. Okay. So these combinations will give you how many ways I can get one head. What is this? How many ways I can get? I can get one head in 4 ways. This is the 4 ways. So that is why I'm putting there 4 ways. When I toss the coin 4 times, 4 choose 1, half to the power 1, 1 minus 1 over half to the power 4 minus 1. So I'm getting this 4 ways is coming from that format. Okay. This 16 is coming from here and there. From here, I'm getting this format. So similarly, 4 choose 2. This 4 choose 2 is giving me how many ways I'm getting 2 head. So that's the way it has been defined. Probability of x equal to n cx p to the power x 1 minus p to the power n minus x, and then here here x takes value 0, 1, 2 up to n, and p is the probability of success. P is the probability of success. Okay. So these coefficients will tell you how many ways you can get the success. So what is x? X equal to number of success. Small x equal to number of successes. So 1 minus p equal to probability of failure. Okay. 1 minus x equal to probability of failure. Now I want to show you 2 things before in next 15 minutes, then I will stop. So first of all, I want to show that this is the 2 criteria, right? This is a binomial distributions I have to prove. First condition is that it is positive. Second condition that it is add up to 1. So probability of x equal to x is always greater equal to 0. Why? N equal to what? Number of success. And n equal to number of trials. Number of trials. Okay. X equal to number of successes. Trial can never be negative, right? Then success can never be negative, right? Probability can never be negative, right? Probability takes value between 0 and 1. 0 means impossible event, and 1 means sure event, right? So that means all things that has been put in a number of trials, number of successes, probability of successes, everything positive. So this is positive. First condition satisfied. Second condition is what? Second condition, I want to prove that this sum to 1. So, so if I plug in there ncx p to the power x 1 minus p to the power n minus x. Okay. Listen, if this is the probability of success and this is the probability of failure, then p plus q equal to what? 1, right? Success probability and failure probability sum to 1, right? So this is equal to 1. Now, if you plug it in there, for example, I just want to put in this format. P plus Q to the power 3. If you plug it in there, then how do you put this? You put this in this format, right? 1 to the power 3 equal to 1. But how do you write this? You write this P cube, you write this 3C0 P to the power 0 q to the power 3 minus 0, 3c1 q to the power 1, q to the power 3 minus 1, 3c2 q to the power 2, q to the power 3 minus 2, and then you write final one, 3c3 q to the power 3, q to the power 3 minus 3. So how many terms you are getting there? Take a look. Here you are getting q cube, and here you getting 3pq square, and there you are getting 3 p square cube, and then here you are getting p cube, right? So now if you plug a value in there and see 0, p to the power 0, 1 minus p to the power n minus 0, and c1 p to the power 1, 1 minus p to the power n minus 1, and then ncn p to the power n, q to the power 1 minus p to the power n minus n. Then if you put all of these things, it will like this format, this equal to that equal to this equal to, then you can write p plus q to the power n, which is equal to 1. Understand? Online people, are you understanding? Okay. So now this properties has been satisfied. Last property I want to tell. Do you remember what I write there? I write there this, right? This is what I want to prove now, then I will stop. Are you seeing I have written something in here, NP? I want to prove this NP. Remember the multiple regression that I showed to you, this is average regression, right? If you take the expectation, why I did not take the expectation? Your classmate asked me, right? When I take the expectation, it is average regression. And this is what? NP. I want to show now NP. Expected value of X. Okay? Expected value of X. Expected value of X could be written as X, P, X equal to X, which could be written as X and CX, P to the power X, 1 minus P to the power N minus X, and X goes 0 to N. Understand? Purpose is to show that this is equal to NP. Then we claim that binomial distribution, expected value of binomial distribution is NP. Purpose is to show that this will give us NP. Understand? You understand? Expected value of X, expected value of binomial distribution is NP. N equal to what? Number of trial. And P equal to what? Probability of success. On an average, if you throw 20 stone to the apple tree, and how many apples you will get? If your success rate is 50%, 20 times 50% equal to 10. If you throw 20 stone to the apple tree, on an average, you will get 10 apples. Are you understanding? The last one, here to there. Yeah. I'm going to derive these things. I just wrote these things. Now I'm going to derive these things. Okay? Purpose is to come there. Now take a look what I am writing. X takes value 0 to n, x, factorial n, factorial x, and minus x. P to the power x, 1 minus p to the power n minus x. Okay? I will come in there. Okay. Now take a look at that. X equal to now 0 to n. Here is x factorial n and x, and then x minus 1 factorial. Then I want to take n minus 1 factorial. Here I want to put here 1. And then I want to put here n minus 1 and x minus 1. X minus 1. And like this. Okay. And then I want to put here p to the power x and p to the power x 1 minus p to the power n minus x minus x p to the power x minus 1 and p. Take a look. This and that become this. This and that become this. This and that become this. This will make that. I did not make any change in there, right? Previously, it starts from 0. Now it starts from 1. Why? Because I take out 1. This cancel out. 1x cancelled out, right? Take a look. In this line, x starts from 0. Right? In this line, x starts from what? 0, right? Why x start from 0? When I defined binomial distribution, how did I define? I defined binomial distributions like this format. X takes value 0 to n, right? This is the definitions. Our forefather 300, 400 years ago, they gave with all rationality. They give rational. When to use binomial distributions? If you are trying to find the success probability when total number of trial is fixed and number of success is fixed and probability of success is given, under these three conditions, total number of trials, number of success and probability of success is given, then you can use this distribution to find the success rate probability. Okay, this is what given by our forefather. So it starts from 0. I cancelled out 1x. I have these things now. So now come in there, this n and this p, I can put it in there. Now I can write here x equal to 1 to n, and then n minus 1 factorial, and then x minus 1 factorial. Then here I can write here n minus x factorial. Then here I can write p to the power x minus 1. Then here I can write p to the power n minus x. See, previously this part, when I write sum of n, x goes 0 to n, then I write here n cx p to the power x 1 minus p to the power n minus x, which I wrote and I showed proof factorial n factorial x n minus x, and then p to the power x 1 minus p to the power n minus x. These things equal to I have shown 1 previously. Now what is the difference? The difference is here it starts 0 to n. Now it starts 1 to n. Here it was n. Here it was n. Now it is n minus 1. Here it is x. Now it is x minus 1. So 1 increase, so there is a decrease in here. 1 decrease, here is an increase in 1. So same thing, right? So that part equal to 1, right? Right? So that means equal to 1. So let me write it. Binomial distribution. Binomial distribution has a mean of NP. Okay. Now, example D. Let me give you an example. Probability of getting an apple from apple tree is 0.40 by stoning. Probability of getting an apple from apple tree is 0.40 by stoning. Okay. If a person threw 40 stones on an average how many apples could be obtained? The total number of trials n equal to what? 40. Okay. Probability of success 0.40, right? So then how many apples he will get? 16, right? Because it has a NP mean, right? And it is mathematically derived, right? So in the next class, what I should do, I will derive Poisson distributions from here. And after deriving Poisson distributions, then I will derive Poisson regressions in this format. At the beginning of the class, I write Y, right? Right? I have to formulate how this come into an existence. I have to write the likelihood functions. In that likelihood functions, I have to plug the Y value, then come into an existence. Okay. Your homework will be easier because this is just the binomial and negative binomial. Next 2 weeks, I'm going to finish. So this week, next 2 weeks, I will derive all mathematics and also discuss like real life problem, how to explain the parameters. So by the end of 5th week, we will have complete derivations and explanation for the Poisson regression and negative binomial regressions. From 6th and 7th week, I will discuss lasso, elastic net, and Rees regressions. Okay. Any questions, comment, problem? I'm going to stop in here. Personal problem that you do not want to share? No?
It's possible to extend the assignment deadline again.
Okay, I extend the homework deadline up until Sunday 11:15. Okay.
Thank you.
Okay. Bye, online people.
Right.